Bismillahirrahmanirrahim. Assalamu alaikum, students. In last lectures, we discussed certain ideas like relative motion, kinetic energy at high speed, linear momentum at high speed, and in a way, we set the environment for studying the special theory of relativity. Today, we will move forward. Now, we will study this theory in detail. First, I want to point out some things about special theory of relativity. I write the spatial theory of relativity, right? One important point about spatial theory, which is important for all readers, is this theory has an undeserved reputation as a difficult subject. That is a good news. It is not mathematically complicated. Most of its details can be understood by you, and we will understand them together. Right? The most challenging aspects of spatial relativity is its insistence that we replace some of our ideas about space and time, which we have acquired through years of common sense experiences, with new ideas. That is the uncomfortable thing about spatial theory of relativity, that we have to replace our ideas of space and time with new ideas, and those new ideas are against our common sense or experiences, right? And you know that essential ideas of spatial relativity were formally presented in a paper written by Albert everybody knows it almost, written by Albert Einstein in 1905. Now, we will present in this unit of our course the basic postulates of Einstein's theory and their consequences. And we will introduce the mathematical techniques that allow measurements made in one frame of reference to be transformed in another. And we will be studying some of the consequences for both kinematics and dynamics, right? We shall start. First thing, if we replace some theory, we know we have classical physics, and it was already there at the time of Albert Einstein. So why we need to extend classical physics using spatial theory of relativity? We need to first understand that. So there must be some shortcomings of classical physics. So we discuss those shortcomings, then we will be discussing how those shortcomings or deficiencies of the classical physics are addressed by spatial theory of relativity. So I write troubles with classical physics. Troubles with classical physics. I request you to listen to me very patiently and keenly. I will go slow as it is important. You know, the kinematics developed by Galileo and then the mechanics developed by Newton, which form the basis of what we call classical physics, had many triumphs. For example, classical physics can be used to understand the motion of planets. We can easily understand the motion of planets using classical physics. So it is one of its triumphs. You can give many examples. I will emphasize another example. We use kinetic theory, which is based on classical physics, to explain the observed properties of gases also. However, a number of experimental phenomena cannot be understood with these otherwise successful classical theories. Now we want to consider few of these difficulties where classical physics fails. So first thing, under this troubles with classical physics, first thing we want to discuss is troubles with our ideas about time. So what is the problem with the idea of time in classical physics? There is a particle called pion. So pion is a particle. Let me use another color. So pion is a particle. Symbolized like this: pi positive or pi negative. It can be negatively charged, it can be positively charged. Now this pion particle can be created in a high energy particle accelerator. So this pion particle can be created in a high energy particle accelerator. It is a very unstable particle. So it is very unstable, right? Now, pions created at rest, listen to me. Pions created at rest are observed to decay to other particles, with an average lifetime of only 26 nanosecond. That is 26 into 10 raised power minus 9 seconds. I repeat, ions created, it is important, when they are created at rest, they are observed to decay to other particles with an average lifetime of only 26 nanosecond. 1 nanosecond is 10 raised power minus 9 seconds. So it is 26 into 10 raised power minus 9 seconds. So they live on the average for this much time. But when they are created at rest. Now in one particular experiment, ions were created in motion. In one particular experiment, ions were created in motion at a speed v equal 0.913 c, where c is what? You know, speed of light. Now in this case, they were observed to travel in the laboratory an average distance of d equaled 17.4 meter before decaying. I repeat, I said, when these pions are created at rest, they live on the average for 26 nanoseconds. But in one particular experiment, they were created in motion at this particular speed, 0.913 c, 913 c, where c is speed of light. And in this case, in this experiment, they were observed to travel in the laboratory an average distance d equal to 17.4 meter before decaying, from which we can conclude that they decay in a time given by d by v. You know, speed is equal to distance over time. So time will be, we take time here, speed will come downstairs. Time will be distance or speed. That means if you divide 17.4 meter over this much speed, you can check it, 63.7 nanosecond. Much larger than the lifetime measured for pions at rest, which is, compare it, 26 nanoseconds. I repeat, when pions are created at rest, they on the average live for only 26 nanoseconds. But when they are created at this speed, they are observed in the laboratory to travel on the average 17.4 meter distance. That means we can conclude that before decay, they live for this much time, 63.7 nanosecond, which is larger compared to 26 nanoseconds, right? This effect is called time dilation, right? And it suggests that something about the relative motion between the pion and the laboratory has stretched the major time interval by a factor of about 2.5. To find the ratio of 26 nanosecond and 63.7 nanosecond, you will get factor as 2.5. Now, such an effect cannot be explained by Newtonian physics, in which time is a universal coordinate having identical values for all observers. So it's one such trouble which cannot be explained using Newtonian physics. Now let us move to second problem. So I write troubles with our ideas about length. Troubles with our ideas about length. Now listen carefully. Suppose an observer in the above discussed laboratory placed one marker at the location of the pions formation. So this is location of pions formation, right? And another at the location of its decay. So another marker at the location of pions decay, right? So there is an observer in the laboratory which we discussed. What the observer does? The observer places one marker here, which is the location of pions formation, and another marker at this in red at the location of pions decay. Now the distance between the markers is measured to be 17.4 meters, as we have already discussed this thing. We said that in the laboratory it was observed that pions travel this much distance before decay. So this distance between these markers is measured to be 17.4 meters, right? Now consider the situation according to a different observer who is traveling along with the pion at the speed at which the pion is traveling with respect to the laboratory. I should write it. Now consider the situation according to a different observer who is traveling along with the pion at speed of u equaled 0.913 c. This is the same speed as that of the pion with respect to the laboratory, right? Now this observer, to whom the pion appears to be at rest, because the observer is traveling with the pion. That means pion is at rest related to this observer. Since for this observer pion is at rest, therefore this observer will measure this observer will measure this observer will measure pion's lifetime to be 26 nanoseconds. Remember, we already said that pions are created at a rest, live only for 26 nanoseconds. Now, since for this observer, this pion is at rest, observer will measure lifetime of the pion to be 26 nanoseconds, which is characteristic of pions at rest. Now, to this observer, distance between the markers showing the formation and decay of the pion is, so this distance, I name this distance for this observer will be how much? This will be speed over time, right? Speed is 0.913 c. Then we divide, not speed over time, speed times time multiplied by time. And you multiply this by 26 nanosecond, what you get 7.1 meter. As speed is distance over time, distance will be speed into time, right? So for this observer who is traveling with the pion at 0.913 second, pion lives only for 26 nanoseconds on the average. Therefore, this distance which I have shown in black for this particular observer will be only 7.1 meter. Thus, two observers who are in relative motion measure different values for the same length interval. Remember, the observer in the laboratory measures the same distance to be 17.4 meter, and the observer moving with the pion measures the same distance between the location of pion's formation and location of pion's decay to be 7.1 meter. 7.1 meter is different than 17.4 meter. What is the conclusion? Conclusion is two observers who are in relative motion measure different values for the same length interval. This is likewise inconsistent with Newtonian physics, in which spatial coordinates are absolute and give identical readings for all observers. Let us move to next issue. So right, third, troubles with our ideas about velocity. I will first draw a figure, then I will explain that. You can draw the figure with me. Figures are always helpful. Draw the figure. This A, B, no. This is A, B, and O. So let me explain. I call it figure 1. Use another color here. The situation is like this. This figure shows a game between A and B as seen by an observer O. So these two people A and B are playing a game, and this is observer O who is observing. So what is the situation? A game between A and B as seen by an observer O, right? Important is we're assuming all three observers are at rest in this reference frame. All three, A, B, and O. All three observers are at rest in this reference frame. So what is the game? A throws a ball. This is ball at superluminal speed, that is faster than light. So A throws a ball at superluminal speed. Superluminal speed means faster than light. Faster than light toward B. Right? So game is A is throwing a ball at a speed faster than that light towards B. Right? And B catches it. B is catching the ball. Now the light signal carrying the wave. Let me first write it here. This is here what? It is light signal showing A throwing ball. Use another color. This is light signal showing A throwing ball. This is same light signal showing A throwing ball. And this one is light signal showing B catching ball. Remember how we observe things? Light gets reflected from an object, then that light signal gets into our eye and we see the image. So when A throws the ball, there will be a light signal showing that scene A throwing ball, right? And that light signal will move at the speed of light in forward direction towards B as well as towards O. I'm showing light signal showing A throwing ball. Now when B catches the ball, there will be another light signal showing B catching ball, right? Now what is the problem? Problem is the light signal carrying the wave of A throwing the ball travels to observer A, as does the light signal carrying the wave of B catching the ball, right? Both light signals travel at speed c. This signal travels at speed c. This signal also travels at speed c, right? Which is less than the speed of the ball thrown by A. Because we are saying that the ball has superluminal speed, it is moving faster than light. So at the location of observer O, the light signal from B, right? The light signal from B arrives before the light signal from A. The light signal from B arrives before the light signal from A. Therefore, according to O, B catches ball before A throws it. I repeat, according to observer O, B catches the ball before A throws it. right? So Newtonian physics permits us to accelerate projectiles like this ball to unlimited velocities, and therefore this Newtonian physics allows such apparent violations of cause and effect to be observed. It's a violation of cause and effect. B cannot catch the ball before A throws it, because first ball will be thrown, then ball will be catched by B, right? So there is a causal relationship between throwing a ball and catching a ball. But since we're seeing this light is traveling at a speed faster than light, so because of that, what will happen? The light signal from B arrives to O before the light signal from A, right? Therefore, according to O, B catches the ball before A throws it. So there is the problem. Now, another thing which I want to mention is, I write it fourth, right? Troubles with our ideas about light. You know Maxwell's theory of electromagnetism? This theory was the greatest triumphs of 19th century physics. And one of the deductions of this theory was that light could be described as an electromagnetic wave, EM wave. And you know, an EM wave, what is the situation? There is an electric field oscillating sinusoidally, right? This is E field variation. Let me use in the color. And there are, so there are E variations, and these are B variation. B stands for magnetic field, E stands for electric field, right? So let these E variations be in XY plane and B variations be in XZ plane. You know, in electromagnetic wave, A is perpendicular to B, electric field is perpendicular to magnetic field, right? So wave will be traveling perpendicular to both. This is the idea of electromagnetic wave, and you know the electromagnetic wave travels at the speed of light, c. So we said that according to Maxwell's theory, light can be described as an electromagnetic wave, right? And just as a mechanical wave can be analyzed in terms of oscillating particles in a medium, an electromagnetic wave can be analyzed in terms of oscillating electric and magnetic fields. So it therefore became a goal of experimental physicists in the late 19th century to detect the medium in which these fields oscillate as light propagates. and to measure speed with which the earth moves through this medium, which was called ether. It was thought that there is a medium which permeates throughout space. That medium is called ether. So these electric and magnetic field variations exist as oscillations in this medium ether, right? So there were experiments conducted to measure the speed with which the earth moves through this medium. Now, beginning in 1881, you know the famous Michelson-Morley experiment. So Michelson and Morley carried out a series of delicate optical experiments to measure the speed with which the earth moves through the postulated ether, right? Now, to their surprise, they found that within their small experimental error, the result was zero. Now, more recent experiments with lasers have improved the precision of this result by many orders of magnitude, and the value remains consistent with zero. Now, given the complex motion of Earth, you know, Earth rotates about its axis and orbits about the Sun as the Sun itself revolves around the center of the galaxy. So, given this complex motion of the Earth, it seems inconceivable that the ether could remain firmly attached to the moving Earth. Yet, great theoretical efforts were made toward the end of the 19th century to try to explain how this could occur. Now, Einstein's brilliant contribution to the understanding of space and time was to show that the concepts of the ether and of the medium of propagation of light were useless and unnecessary, right? I repeat this sentence. Einstein's brilliant contribution to the understanding of space and time was to show that the concepts of ether and of the medium of propagation of light were useless and unnecessary. There is thing called Einstein's paradox. What is that? Now, you know, Einstein proposed his special theory of relativity in 1905. And this he proposed this theory not out of any attempt to explain the outcome of Michelson-Morley experiment, but it was based on a thought experiment that he had devised. What is that thought experiment? Now, as a 16-year-old student, Einstein had learned Maxwell's theory of electromagnetism and had thought about a paradox, which is called Einstein's paradox. Now, what is that paradox? Now, if you paradox goes like this: if you were to move at the speed of light parallel to a light beam traveling in empty space, you would observe static electric and magnetic field patterns. So there's a wave, this is EM wave, right? or light beam traveling in empty space, traveling in empty space, at speed c. Now you are, let me make a cartoon, you are moving with it at c. So if you were to move at the speed of light parallel to a light beam traveling in empty space, what you would observe? You would observe static, electric, and magnetic field patterns. However, Einstein knew that such static, electric, and magnetic field patterns in empty space violated Maxwell's theory. Because according to Maxwell's theory, these electric and magnetic fields, these variations in electromagnetic wave move at speed of light. So you cannot observe them static. Now Einstein was faced with two choices to resolve this paradox. Either Maxwell's theory was wrong, or else the classical kinematics that permits an observer to travel along with the light beam was wrong. So with his intuition, that was perhaps his greatest attribute, Einstein put his faith in Maxwell's theory and sought an alternative to the kinematics of Galileo and Newton. Right? Later in this unit, we show how this new kinematics, which forms the basis of special relativity, prevents any observer from catching a light beam. We also show in the coming lectures how it solves the other problems with time, length, and velocity discussed previously. Now, the critical test of any theory is of course, how well it agrees with experiment. Einstein's spatial theory of relativity has been subjected to exhaustive tests over the past 85 years and uh, more than 85 years and has passed everyone. So, where classical physics and relativity theory predict different results, experiment has always been found to agree with relativity theory. So, I summarize today's lecture. So, first, I discussed with you the trouble with our classical ideas about time, in which time is uh, assumed to be an absolute kind of thing. We said there is a problem, pions created at rest live for 26 nanoseconds, but in an experiment when they are created in motion at this particular speed, they live for 63.7 nanoseconds. It cannot be explained using Newtonian classical physics. Then we discussed the trouble with our idea about length. We saw in this experiment the distance between the location of pions formation and location of pions decay. That distance is measured by an observer in the laboratory to be 17.4 meter, but the observer who moves along with the pion at a speed of 0.913 second, so that pion is at rest related to that observer measures the same distance to be 7.1 meter. Then another trouble we discussed, we said that if there is a game happening between A and B, and observer O is observing the game, A is throwing the ball at superluminant speed faster than light, to another B, A, B, O, all three are observed to be at rest in the frame, concerned reference frame. So what happens? Observer O will observe B catching the ball before A throws the ball. So that is also violation of cause and effect. Then we discussed uh, the trouble with our ideas about light. We said there was postulated a hypothetical medium to explain the propagation of electromagnetic waves, light waves in space, and then attempts were made to measure the speed of Earth relative to the ether or through the ether. And Michelson-Morley experiments and other experiments after that detected that speed to be zero. Then we said Albert Einstein, using new ideas of space and time, using his relativity theory, showed that these ideas of ether were useless and unnecessary. Then we discussed the Einstein's paradox, which led Einstein to propose his new theory. So it was like this, that if you are going parallel to a light beam in empty space at speed of light, you will find these fields to be static, which is against Maxwell's theory, because according to Maxwell's theory, the fields, electric and magnetic fields in light wave or electromagnetic wave, move always at speed of light. So you cannot find them static. So Albert Einstein uh, had two choices, we said, either to discard Maxwell's theory or to discard or extend classical physics of Galileo and Newton. So he supported or confirmed Maxwell's theory and extended the Newtonian physics by his new theory, relativity theory, right? So think about this lecture. I will give you a homework. Let me find a suitable homework for you. Let me find homework. One minute. I had a good question for you. Let me find that. Seven, six. Okay, I have got the question. The question goes like this. A train travels due south due south at 28 meter per second relative to the ground in a rain that is blown to the south by the wind. The path of the, it means another color, the path of each raindrop makes an angle of 64 degree with the vertical. As measured by an observer stationary on the earth. An observer on the train however, sees perfectly vertical tracks vertical tracks of rain on the window pane. Determine the speed of the drops relative to the earth. Let me repeat the question. A train travels due south at 28 meter per second relative to the ground in a rain that is blown to the south by the wind. The path of each raindrop makes an angle of 64 degree with the vertical as measured by an observer stationary on the earth. Now, an observer on the train, however, sees perfectly vertical tracks of rain on the window pane. determine the speed of the drops relative to the Earth. So this is all for today. Do your homework, don't waste your time, and do not forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.